Okay, everybody, welcome to Introductory Astronomy. I'm Professor Hamilton. We're going to start off with a little recording I've made here on my computer before we get to more lectures that are somewhat more face-to-face, or at least me in front of my whiteboard there. Let's start this off here with a sense of scale, of distances in space. After all, in space we're dealing with literally astronomical distances and sizes, so I want to give you an idea of what those look like. Let's start off for saying, how far away is the moon, for example? If we take a look here, use the big red cursor here, I've drawn this to scale. If the Earth is this big, and if you can just see that faint grid underneath my drawing, you see that's one grid space. If the Earth is that big across, then the moon is this big across. It's a little more than 1/4 the diameter of the Earth. And the distance between them is about, pretty darn close to, 30 Earth diameters. So you could count off 30 grid spaces between those there. And when you put it that way, you've probably been used to seeing diagrams of the Earth and the Moon, like if you were watching the Artemis flight, for example, that make it look as if the Moon is much closer to the Earth. Or maybe if you see this distance here, that the Moon Moon and the Earth are bigger in size if you see them drawn that far apart. And so when we put these things to scale, you can just see how much empty space really is out there. So to be more precise, the moon is 29.6 Earth diameters away. And the Earth diameter is 3.7 times bigger than the moon. All right, so we can relate things, one thing to another. We can use the size of one object in space as a unit of size or of distance, for example. And really, that's true for all of our units of measurement. What kind of units do we use? Well, it kind of depends on what we want to use it for. Let's see here. How big is the Earth? Scroll on to this here. How big is the Earth? All right, the Earth's diameter in our common units is 7,900 miles across. Now, your book is going to be using metric for the most part, although there's another system of units that will also have called natural units, like using an Earth diameter or the mass of the sun or something like that. But, and while I'm not, a huge fan of the metric system, this is what the book uses, it's what I use in my research, and we'll be using it here for the most part. To convert from our normal system of units, then, a mile is 1.6 kilometers, give or take a little bit. That is, a kilometer is just a little more than half a mile, 6/10 of a mile there. So as a very rough estimate, if you take the number of miles and you double them and then subtract a little bit, then you've got about the number of kilometers there. So if the Earth is 7,900 miles across, it is 12,700 kilometers across there, and I've rounded off both of these numbers a bit. Now, for the size of the Earth, it's easy enough to use it where we just write the number out in full, separating out a comma to separate out the thousands, for example. But we're very quickly going to get to the point where the distances, the sizes, the masses, whatever, the speeds are so great that we can't really afford to write out hundreds, thousands, millions, billions, trillions of miles, of kilometers, of inches, of whatever, because we're simply going to lose track of all the place value of everything. And for that, we're going to use scientific notation. If it's been a while for you since you've used that, then let me give you a little refresher. If we take the number 12,700 kilometers, the normal way, there are other ways too, but the normal way we would write it in scientific notation is we would take the decimal, which is, I keep wanting to skip over to a editing bar. There's the decimal point, pointing at it there. It's at the end there. These are whole numbers I'm using. And we shift it over, we make it jump over to the left until we've got the first digit, that is the first non-zero digit, to the left of the decimal point, and then all the others to the right. And we don't have to write any trailing zeros at that point then. Then the question is, well, okay, we shifted over, but we've got to still account for the total number there. We shift it over like that. We count how many places the decimal jumps. So 1, 2, 3, 4 to the left to get that 1.27. And so we're multiplying it by 10 to the 4th power. So 10 to the 4th kilometers. If you're making the decimal point jump to the left to make your 1.27, then you have a positive exponent. So 10 here, and it's raised to a power called the exponent. So we'd have a positive 4 for the exponent. On the other hand, what if we had a number like this, 0.00396, and we wanted to write it in scientific notation? Well, once again, we ignore the leading zeros, just like we do the trailing zeros at the other end of the number. So we're going to make 3 jumps to the right. 1, 2, 3. And we put the decimal point right there. And we get 3.96 times 10 to what power? Well, if we're jumping to the right, those are negative numbers for the exponent. So times 10 to the minus 3rd power. Okay, so this is going to make it much, much easier to keep track of how big or how small a number is. The bigger that exponent is, the more positive it is, the larger the number is. The smaller that exponent is, or the more negative it is, then the smaller the number is. For that matter, this brings us to a question of these metric prefixes. You'll see these used all the time in the book. Let's take a little review of this here. I talked about a kilometer. Well, that kilo, the prefix, in which we abbreviate with the letter K, M is for meter, K is for kilo. That kilo has a meaning. Now, there are all kinds of so-called metric prefixes that we use to represent certain exponents, place value, but you're only really going to need to know a few of them in astronomy. In fact, really in any common physics or probably chemistry there, you're only going to need to know these very few here, about 6 or 7 of them. And then there are all kinds of others that you may have been taught at school at one point, but nobody really ever uses, hectodeca, things like that. There are niche cases for those, but we're not going to use them. So the idea is that when we take 10, when that exponent is 10 raised to some power, well, we're really only going to bother with 10 raised to 3, 6, 9, or negative 3, negative 6, negative 9. That is, we're going up in times 3 each time there, which is an extra 1,000, or 1,000,000 is a million, 1,000,000,000 is a billion, and so on. So these 10 to the thirds factors of those there. So a billion, and I've written out a billion here in full. Notice that if we start off here, ones in place value, ones, tens, hundreds, then a comma to give us thousands, 10,000s, 100,000s, another comma gets us millions, 10 millions, 100 millions, a third comma gets us to the billions. Well, if you count up the number of zeros trailing after the 1, that's 10 to the 9th power. That's billions then. And the metric prefix for that is capital G. It has to be capital too, and that stands for giga. So giga means a billion. If we're using the unit of length, the meter, as our whatever it is we're looking at, then a billion meters would be a gigameter. Nobody ever uses that, as far as I'm aware of. If we get to distances like that in space, we're going to start using light years. A million. Okay, 1 followed by 6 zeros. So that's 10 to the 6th power. And capital M, has to be capital, stands for mega, which means million. You would have a megameter. again, which nobody uses. Capital M, lowercase m. Capital M for mega, lowercase m for meters. Thousands, 1 followed by 3 zeros, so 10 to the third. Lowercase k for kilo, and you get kilometer or kilometer. Now, we can also take it down to fractions of a meter. As I said, the ones that we use almost exclusively are factors of 10 to the third, either positive or negative. Thousands, millions, billions, and thousandths, millionths, billionths. But there's one exception to this for common use, and that is a hundredth. So when we write it out, 1/100th, now we got to be careful because we don't have the same number of zeros to the right of the decimal point, although and I will say that you should get in the practice of writing a leading zero before the decimal place when you're writing numbers smaller than 1, because if you don't do that, it's certainly easy to forget the decimal point is there, or you might mistake it for a comma or something like that. So be in the habit of writing that leading zero. All right, so 100th, well, that's 0.01. And so if we were to move the decimal place over 2 places to the right to get a 1.00, that's 10 to the minus second power, 10 to the minus 2. And that prefix is a lowercase c for centi, meaning 100th. Okay, so that's where you get a centimeter, 100th of a meter, and which is roughly 1/3 of an inch. 1,000th, okay, now we're back on more familiar territory, 0.001, so we'd have to move the decimal place over 1, 2, 3 places. 10 to the minus third gets us m. Lowercase m is milli for 1,000th. Millimeter. I admit that the choice of using m for meter here might make it confusing with an m for thousandth, but your prefix is a prefix. It always goes in front of the unit. The unit's always behind it, so you never really can get those mixed up. A millionth, 1, 2, 3, 4, 5, 6 decimal places over, so 10 to the minus 6th. We use the Greek letter mu, M-U. That's a Greek letter M. And the lowercase mu, the capital mu just looks like a capital M, but the lowercase mu stands for micro, and you should be in the habit of learning to write it, because we're going to see that a bit here. It's important when we're dealing with infrared wavelengths of light and maybe sizes of dust grains in space. So this micrometer here is a millionth of a meter. It's pretty small. And that mu is written, if you look carefully, you've got 2 strokes, one downstroke like that, and then you write the next stroke is a little curve that looks like a U attached to it. And really it's just a script letter M that has this long trailing leader sticking down below the line. All right, and finally, the last one that we need to worry about is a billionth. 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places over, so 10 to the minus 9th, and our prefix is a lowercase n, which is nano. We get a nanometer. So a nanometer is a billionth of a meter. Now, we can use these prefixes with any unit, seconds, you could use them with miles for that matter. Energy is measured in joules, so we could have, megajoules or whatever like that. Things like that then. But you'll very frequently see them with lengths. Okay. Now, one more thing before maybe I should use this here. So if we go back to our example of, 12,700 kilometers, that's the size of the Earth. Okay, now I wrote it in kilometers. How many meters would that be? Well, first, let's take this number, 12,700, and we'll write it in scientific notation. Now you should learn to keep the unit with the number at all times. If you separate them out then and just don't write the unit, then the number's kind of meaningless without it. All right? So we move the decimal place over, so we want it to go right behind the 1. So 1, 2, 3, 4 places to the left. So 1.27, we don't have to write the trailing zeros here, times 10 to the 4th power kilometers. Now the thing is that kilometers, that unit at the end, implicitly it's multiplied by the number. It's 1.27 times 10 to the 4th power times a kilometer. It's that many times the length of 1 kilometer. Okay, so that means since 1 kilometer is 1,000 meters, and I am writing it in scientific notation. By the way, yes, you could write 1 times 10 to the 3rd power meters, but you don't have to because it's just times 1, right? Anything times 1 is the thing. All right, so since we're multiplying by the kilometers there, that means we're multiplying by 10 to the 3rd meters. So 1.27 times 10 to the 4th times 10 to the 3rd times meters. What do? Go back to your high school, maybe even your junior high school math. If you're taking powers of 10 multiplied together, you just add their exponents. So 1.27 times 10 to the 4 plus 3rd power meters. 1.27 times 10 to the 7th meters. There. And so now we can see, yeah, in meters it's a lot larger number because a meter is smaller than a kilometer. And this brings up a point. I've been using kilometers, but the basic fundamental unit of length here is the meter itself. And in the metric system, and there is not really any single metric system, despite the kind of, I don't want to go on a rant here, but the sort of metric propaganda that you might get. It's not a perfect system. It's got its flaws there. Its convenience is that you have a lot of powers of 10 that make conversion easier than other systems. But, you know, these days with calculators and computers, then we can convert anything into anything very quickly. So it loses some of its need because we're not having to do this all in our heads anymore. Nevertheless, there are different standards for metric. The trouble is that, well, let's see here. There are 3 fundamental kinds of measurements that you can make about anything in the world. It's length, it's mass, and time. Unfortunately, I forgot to cross the T on time. It looks like lime there. All right, fine, it's time. Now, the meter, we'll use that as our standard unit of length. For mass, you might be more familiar with the gram from a high school science class there. Second, for time, okay. The thing is that meter is actually kind of big. Moderately, meter is it's slightly more than 1 yard. It's a yard plus a tenth. While a gram is a pretty tiny unit of mass. So for laboratory uses, the meter and the gram are kind of at opposite ends of the size scale there, and it's inconvenient. So the great brains who came up with a metric system and thought they had this great perfect system going thought, you know what, this doesn't work for us here. Because when we're trying to measure stuff in the laboratory, it'd be really convenient if the gram is convenient here, but the meter's so big for the little things that we're measuring. So they started doing things with a gram and with the centimeter as the standard unit of length, and the second for time. And so their units for energy and momentum and so on like that were based on centimeter for length, gram for mass, and second for time. That's called the CGS system, centimeter, gram, second. And they would define units of energy called the erg, for example, based around these. And it's a very tiny unit of energy. On the other hand, there are others who are kind of going the outdoorsy types of our scientists, and the meter was a perfectly useful unit of length for them, striding around measuring distances to mountains and whatnot. But the gram was too tiny for, picking up big boulders and whatnot. I'm kind of making up the story here. I'm not entirely sure who came up with this. But so for them, it was more convenient if you paired up the meter with the kilogram for mass, and then the second for time. And so these guys would develop units of energy, which would be the joule. And it's based around the meter and the kilogram in the second. And it's a somewhat larger unit of energy than that little tiny erg is. So you got to pick one or the other there. And we're going to be using this MKS system, meter, kilogram, and second. So the fundamental unit of length is your meter, the fundamental unit of mass is your kilogram, and the fundamental unit of time, not lime, is the second. And all the other metric units that you're going to build up from that are derived from these. Speed, meters per second, although we don't really have a separate name for that. But like I said, you've got energy will be in joules, and that's its own thing based around meters and kilograms and seconds. All right. I will say that in astronomy, though, we have a history of using that other system, centimeters, grams, and seconds. And you might hear me mention some of those units. When we get to them, I'll explain them there. But, it's not anything you're going to worry about now. All right, let's go on then. Let's continue with distances. Okay, so the units that you use are the ones that are convenient for what you're doing. For everyday use, it's useful to use the English system of units or American system, ASE, American Standard English Units, feet, miles, inches, pounds, and so on like that there. And because these are kind of based around human experience, so they're very convenient. Metric units, we'll really use this most in the course there, meters, kilograms, seconds, joules, etc. Have the convenience of converting from one to another fairly easily, but they're not necessarily conveniently sized, and they're really not conveniently sized for astronomy, where, do we want to be carrying around distances where we've got such enormous exponents? So we will also use in astronomy natural units. We base our units on things in nature that are close in scale to what we're talking about. Light years for distance. That is the distance that light travels in 1 year. Light year is a unit of distance, not a unit of time. Solar masses. How heavy, well, really how massive is the sun? 1 solar mass. So we can compare its mass to other stars. We can talk about this star has a mass of 4.7 solar masses, so it's 4.7 times the mass of our sun. Astronomical units, another unit of distance. This is for distances in the solar system. That's the distance from the sun to the earth. That's the astronomical unit, and so on like that then. So natural units are very convenient when you are measuring things out in space. So let's take a look at applying some of these things. The Earth-Moon distance, as I said, can be conveniently measured in Earth diameters. To be a little more precise, it is 29.6 Earth diameters from the Earth to the Moon. That is 234,000 miles. MI is miles. Adding that extra I distinguishes it from the meter, if we're using both. In kilometers, 377,000 kilometers. And if we want to get that to meters, we're probably going to want to put in scientific notation, 3.77 times 10 to the 8th meters. The diameter of the sun, 109 Earth diameters. I didn't draw this to scale just because there's a lot more empty space when you try to scale. If I scale the sun down to one grid square in diameter, I wouldn't have room on the page to put the Earth at all, and the Earth would just be a dot. Sorry, that's really the diameter, not the distance, but true for the distance as well. Because the Earth-Sun distance is 380 times the distance from the Earth to the Moon. Again, look at how much empty space there is out there between when we get out to these larger distances. That's 93 million miles, 150 million kilometers, and it is, by definition, the astronomical unit. AU, capital A, capital U. Sometimes lowercase au, but fine. So the AU is a useful natural unit for measuring distances within our solar system. For example, how far is it from the sun to Pluto? 41 AU, on average. It actually gets a little closer in and a bit farther out over its orbit there. So, we start using these larger scales when we're measuring distances that are larger. What about the distance to the nearest star? Let me scroll that down there. Alpha Centauri, in the constellation Centaurus, the Centaur, it is 26 trillion miles. That's 10, a trillion is 10 to the 12th power. Enormous. I didn't cover trillions because we don't really, in the metric prefixes, because we don't really use the trillion metric prefix very much in astronomy. Occasionally, but not very often. And so you don't need to worry about it. But it's a big number. In astronomical units, 275,000 AU. Again, that AU is the distance from the Earth to the Sun, so we're in 250,000 AUs away from the Sun, and then some. But what have we measured in light years? Aha! Very convenient there. That star is 4.4, about 4.5 light years away from Earth. And we'll use Ly is the light year. Again, the distance light travels in a year. There. Okay. Which is 5.9 trillion miles, just shy of 6 trillion miles, or 9.5 trillion kilometers, almost 10 trillion kilometers. We can write that as 9.5 times 10 to the 12th kilometers there, or times 10 to the 15th for meters. So this is the distance that is the unit of distance that is very useful for measuring distances to stars, or even to galaxies then. You'll find as we get farther on, there's even another unit of distance that's a little bit bigger called the parsec, which is about 3.25 light years. But we'll get to that later on then. Okay, let's take a look at the size of the Milky Way. And that's our last bit for this section here. So the Milky Way is our galaxy. It has somewhere on the order of 300 billion stars in it. And it is roughly, notice that my equal sign here is a squiggly equal sign. That means approximately equal to. Let me scroll back up here. You might have noticed at the top that the Earth to Moon, that's about 30 Earth diameters. Here I put a single squiggly line, which is even rougher, even more approximately. Actually, that's almost exactly 30 there. Maybe I should have used the single squiggly line for the size of the Milky Way there, because that's much more rounded off. There's not really a hard edge to it as well. Anyway, it's about 100,000 light years across. Okay, just a nice round number. We could be off by a factor of 2 or something there because of that lack of a hard edge. But how far away is the Andromeda Galaxy? That one we can measure more carefully. 2,300,000 light years. That's 23 Milky Way diameters away. So if I were to draw these two to scale, the Andromeda Galaxy here is a bit bigger than the Milky Way. Here the Milky Way is 100,000 light years across, that's that distance, and they are separated by 23 Milky Way diameters. If you took out quarters, 1 quarter to represent the Milky Way, 1 to represent the Andromeda Galaxy, put 23 quarter spaces in between them there. Actually, the funny thing is that when you get up to this much bigger scale in space, you see that space is a bit more crowded. That is, we don't have, these galaxies are not little tiny pinpoints with all that empty space between them. They're actually kind of big. The space between them is not unimaginably huge compared to the size of the galaxies themselves. Anyway, just something for you to think about there. Now, I am doing this, the way I'm arranging this is, we're going to have a bit of math in this, but not all that much. I'm going to introduce any math concepts that you need to be reminded of as we use them, as we get to them. And most of the math you're going to do is going to be in lab projects where you'll be instructed step-by-step in calculations. You're not going to be doing as much on open-ended problem solving for math here. But the There is, nevertheless, a problem-solving guide I've written for you in case there are any problems that you do have to solve. And at the beginning of it is a math review, which is in detail. And if it's been a while since you've had a math class, which is true for many of you, refer back to this. It'll have pretty much everything that you need. And actually, it goes into more detail than you're actually going to need. There is one other concept that I should bring up while we're on this topic, and that is the concept of the number of significant figures in a number. Let's go back here. Take a look at this distance, the diameter of the Earth, 12,700 kilometers. This, we would say, is written with three significant figures, the 1, 2, and the 7. Now, significant means they are known more or less precisely. We're not rounding them off. But notice that it's 12,700. You might get a clue that that 700 is rounded off there, that those two trailing zeros are kind of made up. That is, the distance is not exactly 12,700. It's probably, there probably are some other digits after that 7, which we have not measured, or, well, somebody's measured them. But I've simply rounded it off to the nearest 100. So those zeros are not significant then. Only the 1, 2, and the 7 are. So when we write it in scientific notation, it's actually a bit easier to see. We only write those significant figures. So that 1.27, we strip away those trailing zeros, because we really didn't know what should go there anyway, and just write the significant figures. So 3 significant figures here. So we ignore trailing zeros, but if it was like 12,701 kilometer, that would tell you that the middle zero is significant after all, because there is another digit at the end of it there. Admittedly, this is sort of a human convention. It's nothing really magical about it. You could have it where the answer was exactly 12,700, and admittedly, it would be confusing for people unless you specify that that was an exact number. Don't worry about it here, though. If you have, so let's see, these millions, thousands, billions that I've written up here, all of these just have one significant figure, which is the 1. And all of those trailing zeros are ignored. Okay? What about leading zeros, that is, on the left-hand side? Those are not significant either. If there are only zeros to the left of another number, then all of those zeros are not significant. If, on the other hand, you had, like, let's say this 100th, if you had 1.01, all of those would be significant. Now, I don't want to belabor this point very much, but if you ever need to do some calculation, you really can't justify putting, 20 decimal places in your answer, even if your calculator gave them to you. I guess calculators don't really give 20 decimal places, maybe 10. But don't overdo these things then. With the kinds of measurements that you're going to be making, like on a lab project, if you need to measure the size of something, you're not really going to be putting, it is 1.2765321.573 centimeters across or something like that. That's kind of ridiculous because, in a sense, you're claiming you can measure it down to that last digit there in precision, and you really can't. So that's why we're going to round these things off to 2 or 3 significant figures in the end. Although it's best to wait and round things off when you do get to the end of a calculation. Again, we're not going to do a whole lot of the calculations of that sort then, but you'll have some. And that is the end of this first lesson on sizes, distances, scales, and a little bit of review of numbers.